All right, this is materials testing. This is our stress and strain calculations, and we're going to be looking at problem number 5. The problem is a 35-foot long steel rod is subjected to a load of 8,000 pounds. This load causes the rod to stretch 0.266 inches. The modulus of elasticity of the steel is 30 million psi. Determine the diameter of the rod. Keep your precision to the hundredths place. All right. So what we're going to do is we're going to go through the problem and actually list our knowns. So we come to our first one, which is 35 feet. I am going to see that there's inches in other spots. So we've got 0.266 inches, and psi is also another inch. So I'm going to convert that directly to inches right off the bat, giving me 420 inches. Reading along, I get up to 8,000 pounds. 8,000 pounds is going to match my force that I'm putting on the load. The next thing is my 0.266 inches, which is my stretch. So that talks about my elongation. I'm going to represent that with delta. Then I have my modulus of elasticity. The variable for that is E, and that's going to be 30 million. Last thing is, so I've listed all my numbers in the problem as what they could be. I've got to determine what the diameter of the rod is the question. So let me bring that in. My unknown is D, and so I need to solve for that. So let's move those up, and we'll look at the equations that we have. The nice thing is I sort of have to work back a little bit. So I have D here. Only one of my equations have D, so I know I'm going right there off the bat. I don't have the R, so I need to look at equations that have R also. So let's see here. Right there, that's the only one, so I'm going to go straight to that one. I'm also going to list R up here, something that I don't know, because I need to figure that out. In this equation now, I have A. I don't have A up here either, so I need to add A in, and I also need to determine which one of these has A that I can work with. So I've got 1, 2, 3, 4 A's to look at. Let's just do process of elimination. I need to only not know the A, so I need to know the L and the W. I don't know what W is. I really don't know what L is because it's a different length than what I need there. Right here, I don't know the sigma. And I do know my force, which is 8,000, but that cancels out that equation. I don't know tau here, so that doesn't help me there. When I finally get over to this equation, I've got my elasticity, which is 30 million. I've got my force, which is 8,000. My length is 420 inches, and my delta is 0.266. So I can actually use this equation here. So let's go ahead and we'll list all our equations that we found out that we needed, and I've got it to where I'm going from bottom to top here. So I'm going to just write my numbers in that I just said into it. So I've got my 30 million equals 8,000 times 420 over my area times 0.266. Now, what I'm going to have to do is I'm going to have to think of that as being over 1, and I'm going to just cross multiply here. So that gives me this long expression here. And to get it to where we just have A by itself, anything that is not A on this side, I'm going to divide from both sides. So that gives me this right here. Now I'm in the spot where I can actually type this into my calculator and work with it. So we move on, and I get this value right here, which is 0.421. I did do a simplification step here just to help me type it in. It depends whether or not I have a graphing calculator. If I had a graphing calculator, I'd probably type this whole thing in here. So I'm going to plug this in up here, all right, and we're going to look at solving up for our R. All right, so my equation was pi r squared, which is the standard area for a circle. I'm going to have to get rid of my square by get rid of my pi by dividing both sides by pi. So that puts the pi on the bottom here. And I have to get rid of my square by taking the square root of each side. So what needs to happen is I then plug those numbers in. So I've got 0.421 over pi, and when I type that into my calculator, I get 0.366. All right, I can now plug that in for my R and solve for my diameter, which is what my initial problem was. So if I get that, I have 2 times 0.366, sorry. That gives me 0.73. The nice thing, it is already in the precision down to the hundredths place, so I'm done with my problem here, and that's a very good thing.